All right, welcome back to the last portion of chapter three, and now we will be discussing the geometric design of highways. And to be more specific, we will be talking today about the horizontal alignments as well as the concept of super elevation. So today's objective, we are trying first to define the what I mean by super elevation, and then we're going to explain the super elevation design, and then of course we're going to explain the horizontal alignment and the horizontal curve design equations. So by definition, the horizontal alignment is basically, as I mentioned to you earlier in earlier lectures, is the projection of the facility on the horizontal on a horizontal plane. If I'm looking at it from the top, if I'm on a plane looking downward on the street, any curvature seen, that's what we call a horizontal alignment. So it's any horizontal curve. It's gonna generally consist of a straight line first, which is the tangent, and then it's gonna be connected by a circular curves, either directly, such as if it's a simple curve, or via intermediate transition curves. So sometimes we may have this what we call transition curve, or it can be from a tangent directly to a simple circular curve and then back to the tangent one more time. So the way we derive the horizontal alignment concept, it's very related to the concept of centripetal force and the super elevation. So the critical design feature of any horizontal alignment is the horizontal curve um, that transitions actually the roadway between two straight tangents. And that's the goal. Is again, I have a tangent and I have a curve and I have a tangent, and the goal is while the vehicle is going through this horizontal alignment, we're interested to understand what we call the vehicle cornering, or the side force capability, is actually one of the key concern in any horizontal design factor. So imagine again you're driving on a horizontal curve, and RV, this is actually the radius of that radius of the vertical curve, and then there will be some sort of super elevation, and that's the alpha here. So without that super elevation, by the laws of physics, if you're driving at even a certain speed, you can be actually going out um, of that curvatures, and that's why we have the concept of super elevation to keep you inside. We see this more in car racing competitions, where the cars are almost like the super elevation, or that angle is very high because it's proportionate to the speed of the vehicle. And if you are racing, you are at much higher speeds, and without that super elevation, that angle right here, again the car will be drifting off of the curvature. So what do we see in more details in this picture again? First of all, RV, as I mentioned a couple seconds ago, RV, this is the radius defined as the vehicle travel path, and it's either in feet or meters. Alpha, this is the angle of incline in degrees. And then we have, this is the alpha right here. And then we have the E. This is the E right here, which is the number of vertical feet of rise per 100 feet of horizontal distance. So this is actually over there is the relationship between the alpha and the E. So alpha is the angle, and then E over 100. That's again, we can correlate this to the alpha, the tangent of that actually. So tangent, we're gonna discuss it later, but let me write it down here. Tangent alpha again is gonna be equal to E over 100. So the E, in a simple term, again, it's number of vehicle, the distance in the vertical direction, while once we ride 100 feet of horizontal distance. The W, again, that's easy. The W is the weight of the vehicle, and then the weight, of course, as we got to know in physics, it has two components: the Wn and the Wp. The Wn and the Wp. That is the Wp, and that's the Wn. Wn, this is the weight of the vehicle normal to the roadway surface, and it's in pounds or in Newton, depending on the units you are using. And the Wp, this is the vehicle weight, which is parallel to the roadway surface, and it's in pounds as well. FF, which is right here. This is actually the side frictional force, centripetal force. This is the friction between the tire of the vehicle and the side, or the surface of the vehicle, the surface of the roadway itself. FC, which is right here, this is the centripetal force. So the centripetal force, which is the lateral acceleration x which times the mass of the vehicle. So when you really multiply the lateral acceleration times the mass, is gonna get you the centripetal force, and that centripetal force also is having two components, F and C, and FCN and FCP. FCP, this is the centripetal force acting parallel to the roadway surface, and FCN, this is the centripetal force acting normal to the roadway surface. And the reason why we're showing you all these factors, this is what we're gonna try to derive. The bottom line is really, I'm interested in this right here. What is that radius of the horizontal curve? Remember, back in the vertical curves, we were interested in the L, the length of the curve, the length of the vertical curve. In the horizontal alignment is all about the radius of that curvature. So, and that's what we're gonna go through here, some derivation to come to the last equation that we're gonna use later on. But for basic horizontal curve relationship, if you really do um, the balance of forces in one of the two directions, we are gonna find out that the WP, the weight of the vehicle in the parallel direction, plus FF is gonna equal to FCP. And basically, from basic physics, the equation can be actually rewritten as follows, and we can actually expand that equation simply because FF is actually, it's Fs times Wm plus Fcn. So if we replace that, so Wp, the weight of the vehicle, and the parallel direction, which is gonna be W sine alpha, plus Ff is now we're replacing it by S times Wm plus Fcn. So Fs, that's constant, which is the coefficient of side friction. That's always constant, is going to be given to you, times W cosine theta, cosine alpha. That's the normal component of the weight of the vehicle, plus WV square over G times RV times sine alpha. This is the centripetal force in the normal direction. This is from physics as well. You can go back to physics to get the what is the centripetal force. This all has to be equal to this FCP. FCP, again, this is the centripetal force in the parallel direction, which is it's nothing different than the than the FCN, except now it's cosine alpha. So it's again the weight of the vehicle times the speed of the vehicle squared over G, 32.2 or 9.81, times RV, the radius of the curvature, times cosine alpha. So looking at that equation, we are after mainly the RV right here. So we really want to get the equation in terms of an RV. What we're seeing in this equation, we could see that there is weight of the vehicle is important, the angle, which is the super elevation, is important, and of course the speed. So you could tell from now we are heading towards an equation that is RV as a function of the weight of the vehicle, the super elevation, as well as the speed. And how can we do this? Basically, we're going to simplify the equation. And if we really divide both sides of the previous equation by W cosine theta, we're going to yield to this simple equation right here. The tangent of alpha plus Fs equal to V squared over G times RV, all that times 1 minus Fs times tangent of alpha. And we got to know that again, tangent of alpha is actually referred to as the super elevation, the tangent, and that's what I defined for you here. The tangent of alpha, this whole thing, we call it, that's the super elevation. It's not the alpha itself, the tangent of it is the super elevation. So again, the term alpha is referred to the super elevation of the curve and is denoted as E, which is again E. If you do the math, is going to be equal to 100 times tangent of alpha. Where did we get that from? You can go back to here. Again, if tangent alpha equal to E over 100, so E is actually equal to 100 times tangent alpha. So if we have that, we can replace it here. We can replace this relationship in this equation, and also being conservative and also ignoring the normal component of the centripetal force, which is Fs times tangent alpha, and with E is equal to again 100 times tangent alpha. The above equation now can be, we can rearrange it, and we're going to end up with this equation that's very important to us as designers of horizontal alignment. So the radius of the horizontal alignment is basically depending on the speed, v squared over g, so v squared over g times fs plus e over h, e over 100. So as I told you, the radius of the horizontal alignment heavily depends on mainly the speed, because again to the power, to the second power, but also depend on the fs, the friction, as well as the e over 100, which is the super elevation. So, and the goal, as always, we need to select the minimum radius, as we did for the vertical alignment, where we we're designing for LM, the minimum length, because the minimum length, that means this is the minimum amount of cut and fill I'm gonna have in any new location constructing that roadway. Same thing with the horizontal alignment. I would be looking into the minimal radius. So selected value, and speaking of that, again, how are we selecting the value of the E is very critical, because again, the speed limit, I can set that as again, as an engineer, I put the speed limit, but selecting the E, the super elevation, is critical. Why? Because high rates of super elevation can actually cause the vehicle steering problems on the horizontal curve. And in cold climates, or again, when we see ice, mainly on the roadway, this can reduce the FS, the friction, such as that vehicles traveling now less than the design speed on an excessively super elevated curve, actually they could slide inward. So it's the opposite. So again, if I really have high alpha here, or high super elevation, and if the vehicle again driving this direction, again along that curvature, and if this vehicle is at lower speed, it actually is gonna drift to inward instead of outward. So it's gonna drift inward if the speed is low, and it can eventually drift outward if the speed is high. So really now it's all about how can I pick the minimum radius, is depending on selecting appropriate super elevation, which is E, and the design speed, which is the V, and using again the maximum side friction, Fs, to obtain again the minimum radius possible. So what Ashton did, similar to what they try to do for the vertical alignment, to make the life of transportation engineers a little better, is actually they came up with table 3.3.5 that gives the Ashton the guidelines for selecting values of E and Fs. This is here an example of what I'm talking about, which is basically table 3.5 tells you what's the minimum radius using limiting value of E and Fs. So really, first, again, the first column here, it gives you the design speed. So we have, again, this is from 10 miles per hour all the way to 60 miles per hour. And then basically the second column would be the maximum E, the super elevation is 4%. And then this is the limiting value of Fs. And then you go all the way until you have now the calculated radius. This is the radius needed, or this is the rounded radius. This is actually the what we're gonna be reporting. And then, and instead of just, if you are designing maximum super elevation at 4%, this is the only place that you're gonna go to. If you're designing the super elevation at 6%, you will be using this part of the table. And again, the speeds are the same from 10 till 80 miles per hour, or you can use 8%, or you can use 10%, all the way to 12%. So as you could see, this table has capability of um, giving you what's the rounded radius, RV, the minimum radius, knowing the speed limit of that roadway that you're designing, and what's the maximum super elevation. So it's pretty handy, and I highly recommend you to use if needed. The curve options, the horizontal curve options that we have, there are actually a few options available for curve types to connect tangent sections. We are gonna be concentrating more on the circular, simple circular curve, which is that's the most popular. Basically, it's connecting a tangent to a curve to a tangent. Or we can also have reverse curve, which is actually interesting one. Reverse curve is actually I have a curvature and then I have a reversed one right away without having any tangent in the middle. Compound curve, that's actually a curve, two curves after each other with different radii, for which is basically assuming that you have this curve and you have another curve. So this very first one is going to have an RV1, and the second one here is going to have an RV2. It's compound curve. Spiral curve, as the word says, again, spiral curve, really, again, I have one curvature and another curvature. We use this a lot when we are designing horizontal curves in a very mountainous area where we can't afford having a tangent or even just reverse the curve. It's just going to be spirally like what you see here. In this course, again, we'll be focusing more on the simple circular curve. Most of the time, that's what we end up designing anyways, except if we're really forced to do something different. So the circular curve has a single constant radius, as I mentioned. So here, this is here the RV. The RV is constant across the board. And the following figure, again, that I'm going to show you, this shows you the basic elements of a simple circular curve. So this is here the major components of simple circular horizontal curve. Um, and I'm gonna define for you every one of these components. So the very first one that we just talked about is the R. This is the radius. The radius, which is usually measured to the center line of the roadway, and that's in feet. And then we have alpha, I mean delta. So delta over 2, if you sum up these two, we're going to have the big delta, which is the center angle of the curve in degrees. And then PC, this is here the beginning of the curvature, or technically we call the point of curve PC. It's the beginning point of the horizontal curve. And then we have PI right here. That's the point of tangent where the two tangents are meeting. And the PT, this is the point of tangent, which is the end point of the horizontal curve. And then we have T. This is the T right here. This is the tangent length. And then we have other little components that we like to define, which is the middle ordinate, M, and the E. This is the external distance, which is the distance from this point here to the imaginary PT. That's the E. And then of course L, this is the length of the curve. And in this case, which is different than the vertical curve, the length of the horizontal curve is along the curvature, which is again vertical curves we used to measure from the horizontal, which is just again straight line, but the length of the curve here for simple circular horizontal curve is along that curvature. The equations are already derived for you. You can usually simply, again, we derived all the equations based on some of those similar triangles that we have here. So they are easy to derive, and the equations are provided to you here, and they will be provided to you in the exam or an FE exam. The D, that's actually another thing that I did not mention before. The degree is, this is the degree of curvature. It's an angle subtended by 100 feet arc along the horizontal curve. We typically um, like to measure it. It's a sort of measurement of how sharp is the curvature. But more importantly, we're interested to know the tangent of that horizontal curve. I'm interested to get the E, the M, and of course the length of the curve. You're gonna ask me what is the equation for R? The R again is will be defined earlier by the table. So you can get the R. Once you get the R, really, if you know the R and if you know the delta, you can get the T, and then the E also, depending on the R and the cosine of alpha, I mean delta over 2. Same thing with M, all the way to L. The length of the curve is pi over 100, 180 times R times delta. One last thing here, that's now is gonna affect the stopping side to the stopping side distance is and the horizontal curve is the following case. If I have any side obstruction here, take a look at this here. This is the side obstruction. So if you're starting to drive at the beginning of the curve and you're driving along that curve, you are now, the side distance is going to be actually not the whole length of the curve. It's going to be now affected highly by that obstruction. It can be a tree, it can be a billboard, it can be anything. So side distance restriction on horizontal curve occur actually when these obstructions are present as shown in the picture. So when such an obstruction exists, the stopping side distance is actually now starting to be measured along the horizontal curve from the center of the travel lane. From the center of the travel lane. As you can see here now, I'm assuming that we assume the assumed location of the driver I. Basically, it's the center of the travel lane. So making this again, zooming in into this situation and seeing what's going on here, this is now for this is what's going on. So if we have an obstruction here, this is now the available side distance, and the eye of the driver will be again in the middle of that lane driving. And now our goal, I'm interested now to know what's that ms, what's that distance. I need to decide what's the minimum distance that I have to keep cleared. And this is why again you see most of the time the trees or the billboard, they have to be away from the side of the roadway by certain distance, because that ms is going to define for me what's the available stopping side distance. So for a specified stopping side distance, some distance, which is the ms, which is the middle ordinate now of the curve, has an arc length equal to the stopping side distance, must be visually cleared. Nothing is there. That So again, it has to be clear so that the line of sight is such that sufficient stopping distance is really available. And the equations are here for you. They are defined for you already. The SST, the stopping side distance, is equal to pi over 180 times RV times alpha S. I mean delta S. Therefore, the delta S, which is now, see, and instead of having now the full delta, if nothing is obstructing our vision, now we're having now a restricted delta. This is the site delta, delta S, the site delta. And now if the site delta is known and we multiply by RV, I'm gonna get now the stopping side distance. So here, this is really if I'm designing the roadway. If you're designing the roadway, uh, um, you're going to use actually this equation. So delta S is in terms of SSD. So you can really play with this equation here to move everything on one side and delta S on the other side. So it depends on the situation, if you're designing versus analyzing. Um, so you can, if you know what's the available side distance, you're going to be able to define what's the minimum delta S, or if you know the delta S, you'll be able to get the SSD. So if you really now use these two equations, and if you're substituting into the general equation, which is for the middle ordinate, a simple horizontal curve will give us this equation, ms. Now this is now you're designing the roadway. This is the minimum clearance that you have to have, the minimum clearance that you have to have in order to achieve the minimum site distance. So the ms is equal to rv times 1 minus cosine 90 times ssd over pi rv. If you are trying now to solve the this equation to get the ssd, now this is an analysis part. So this here is a design. You can design the structure. Designing the structure is going to require for you to design what's the maximum minimum clearance on the edges of on the sides of the roadway. But now if an accident happened, and now you want to analyze the situation, what's going on, what may have caused the problem, if we have an obstruction on the side of the roadway. So you know what's your ms already. If there is a tree very close to the roadway and you're suspecting that this might affect the negatively the situation, then you know what's your ms, because the obstruction is there, and you can measure that distance from the tree to the edge of the roadway, or actually to the center of the lane. That's the ms, and you know the radius, and in this case you will be able to know what's the available site distance at that location. And of course you're going to compare it to the minimal amount of site distance that you have to have at this roadway, and then you'll be able to judge whether or not there was a problem there, or do we need to cut that tree or move that billboard away from away from this roadway in order to increase the ms. Because if you increase the ms, the site distance now will be much more, or at least again you will have if the ms if there's no trees away, then the site distance needed actually is less, because um, now everything is cleared and you will be able to see a lot. So that's what I'm trying to say is the whether you're designing, you're going to use the ms. This is for design purposes, and if you are analyzing the situation, that what we'll be using. So if you want to get more details on this horizontal alignment, you can go to chapter 3.4, and that's where you'll find the most of the information. Next time again, we'll get going with chapter 5. Before I get going again, a summary of this little mini lecture here for the horizontal alignment. What we've done, as again a little recap: we defined the super elevation, and then what's the super elevation design, and we defined the horizontal alignment and the horizontal curve. We defined it. It's basically any curvature. So from a tangent to a curvature. And horizontal alignment, how can we detect the horizontal alignment? So looking at it from a plane view. So this is the definition, and then the whole goal is actually to design the radius of that curve. The radius of the curve is basically is a function of three factors: the speed of the vehicle, the friction between the vehicle and the roadway surface, as well as the super elevation. We got to know that there is a table developed by ASHTO, table 3.5, to define for us the minimum radius using the speed limit and the maximum super elevation. And again, we have multiple values for super elevation here. It can go from 4% all the way to 12%, which is quite high. So you have a big range to pick from in this table. And then we got to know that there are multiple options for horizontal curve, but the one that we covered today is the simple circular curve. And then the equations are going to be provided to you. They are all here. And then the last thing that we mentioned is, if we have an obstruction like what you see here, now this is going to define for us what's the site distance available at that location. So we have two equations. See here again, it all depends on the eye of the driver in the middle of the lane. And so the distance from the eye of the driver all the way to the obstruction, this is what's going to be defining for us the site distance available. So if you are really now trying to design a brand new road, you know what is the minimum site distance. So what you're going to be designing for is actually designing the minimum clearance that you need to have. So the site distance will be already set, and the radius of the curve is already set. The only thing that's missing is the ms. What's the ms that you need to keep cleared? But if you are analyzing an existing roadway, that something happened to it, an accident happened, and we're trying to find what's the main problem with that accident, then the ms is known, because now you go to the location of the incident, and you know what's the distance between the closest obstruction of the to the mid lane, and that is known, and you know the radius of the curvature. Now you're going to be assessing what's the true stopping site distance at this location, and whether or not this is meeting the minimum specs. So again, with that, we finished again this chapter. Basically, we covered two major components of any highway geometric design, which is the vertical and horizontal alignments. Thank you so much. And again, we will talk and see you in the next chapter, chapter 5. Thank you.